Hello Physical Science, this is Mr. B, and we are moving on today with Section 3, and the title of this section is The Modern Atomic Theory. So up to this point, we talked about some work that a lot of scientists did in the past that kind of helped move us along to our understanding of what atoms are, and not necessarily each one of them, each one of them kind of had a piece of the puzzle correct, but none of them really up to this point had every single part of this atomic theory correct. So now we're going to talk about maybe some work of some more scientists that helped us lead to our understanding of what we know today. So things that are more modern, things that are more accepted than the scientists that we've talked about so far. Again, it's not to say that those other scientists weren't as important, but now we're just kind of take a step into the realm of where we are at today. And so to start, again, it always asks us a question here, and this is a pretty cool example of why we need to know about our modern atomic theory, because it talks about firework colors, and they're wondering why different fireworks are different colors are shown up in fireworks displays. And certain compounds will produce certain colors of light when they are heated. Compounds containing the element strontium produce red light. Compounds containing barium produce green light. And so we're going to take a look, or we're going to find out here, I think by the end of this video, about how electrons actually play a role in the heating and the energy change and the releasing the different colors. So we're going to, by the end of this video, know why fireworks show different colors in different displays. And it's going to actually be and this is going to be based off a guy by the last name of Bohr. We're going to talk about him. And what he kind of took a look at is electrons. That was his main focus. So our big question that we're going to ask is what happens to electrons when atoms gain or lose energy. So Bohr's model of an atom. So as did Rutherford's atomic model, Bohr's atomic model had a nucleus surrounding. And Mrs. B just tried to say that Bohr is boring, but that is not the case at all, because he was very important, because his model focused on the electrons and their arrangement. So they pretty much knew that they had the nucleus correct, so now they need to figure out what was going on with the electrons in the space outside of the nucleus. And in Bohr's model, electrons move with constant speed in fixed orbits around the nucleus, like planets around a sun. So each electron in an atom has a specific amount of energy. So in Bohr's model, he kind of make it a real life comparison. He made the nucleus was kind of like the sun, and the electrons orbited around the nucleus like planets orbit around the sun. And each electron can have a specific amount of energy. That's going to take a play in here. We're going to explain that a little more. And when an atom gains or loses energy, the energy of the electron can change as well. So when the atom, again, when energy is added to the atom as a whole, it can actually directly add energy to the electrons as well. And the possible energies that electrons in an atom can have are called energy levels. That's pretty self-explanatory, so I'd make sure I wrote that down. So there's something that are called energy levels that exist between electrons, and a way that you can kind of make that as a comparison, that energy levels are like different orbits. So it's almost like okay, I'm getting a little ahead of myself. And it says an electron cannot exist between energy levels, meaning that electrons have to stay in a certain energy level. There's no way they can kind of like be halfway between the first energy level and the second energy level. It doesn't work like that. They have to be in these distinct energy levels. And what an energy level kind of looks like, it's kind of like each energy level is like a different path, like a different planet orbiting the sun. So if you look here, we have the nucleus, and we can see there's two energy levels surrounding it, and you can see we have 2 electrons in our first energy level, and we have 1, 2, 3, 4, 5, 6 electrons in our second energy level. And what it is saying is when atoms gain or lose energy, they can jump between these two different rings. So if this atom gains a bunch of energy, then maybe these 2 electrons will jump out of the first energy level into the second energy level. Or if for some reason, if the atom is going to lose energy, then maybe these electrons will jump down into the first energy level. It's not like they can exist halfway in between. They have to be within each energy level. And kind of an example to kind of go back to the sun orbiting the the planets orbiting the sun is almost like Well, let's say this is Mercury, this is the closest planet to the Sun, and then we have Venus. Well, let's say all of a sudden a bunch of energy is added to the universe. Well, Mercury is going to jump up, and it's going to jump into the same path that Venus is orbiting the Sun in. I mean, that's kind of a weird comparison. That's obviously not how it works, but that's kind of to relate them to one another, kind of what's going on here. And then they give another analogy for energy levels. It's kind of like a staircase. So the landing at the bottom of the staircase is the lowest level. So they're saying this is like the bottom of the staircase. So basically like your floor. And each step up represents a higher energy level. So as you're walking up, as you're walking up the stairs, it's like you're moving up to the different higher energy levels. And the step height represents an energy difference between levels. So again, it's like you have to move up in height, and you're actually moving up in energy as well. And you can only move in whole numbers of stairs. It's not like you can move half a stair at a time. That literally is just physically impossible. There's no half stairs, at least that I've seen any time in my life. And an electron may move up or down 2 or more energy levels if it gains or loses the right amount of energy. So going back to here, we can pretend that there's a third line out here, a third circle, and if enough energy is added, then it can jump from this first one, it can skip over that second one into the third one. Just like if you get enough speed going, you can jump up 2 stairs at a time. And the size of the jump between energy levels determines the amount of energy gained or lost. So if we jump from the second or the first one to the third one, that means we had a big increase in energy. And then kind of on the flip side of that, if we go from the third one all the way down to the first one, that means we're going to have a little, or no, I'm sorry, not a little, we're going to have a big loss of energy. And no two elements have the same set of energy levels, so they're all going to be different between each example. Sorry, and so for evidence for energy levels, so the reason why we know these actually exist, because like I said, it's not like we can actually see these electrons and these perfect, it's not like there's these actual rings that these electrons are traveling along, is scientists can measure the energy that's gained when electrons absorb energy and move to a higher energy level, or they measure the energy released when the electron moves to a lower energy level. And light is a form of energy that can be observed. So scientists can actually measure the amount of energy gained or lost when these electrons absorb energy or when they release energy, and one way they can tell is that light is a form of energy that can be observed. And the movement of electrons between energy levels explains the light you see when fireworks explode. So again, this is kind of tying back into why we need to actually know about these energy levels, because there's a lot of real-world applications here. It says heat causes some electrons to move to higher energy levels. So when those electrons move back to the low energy levels, they release energy, and some of that energy is released as visible light. So and then different elements emit different colors of light because no two elements have the same set of energy levels. So how that works is, again, the heat causes the electrons to move to higher energy levels. So that's probably as it's going up. Again, you light the fuse shoots up in the air, and when it explodes, that's going to be a bunch of heat is going to be added to those electrons all at once. So that as that happens, all the electrons move up into different energy levels. However, that heat is not sustained. It doesn't last very long. So as that heat starts to dissipate after the explosions occurred, then all of a sudden those electrons that jumped up really quickly, now that they're going to move back down, and as they move down, they're releasing energy, and when they release energy, some of it is visible light, and they turn different colors because no two elements have the same set of energy levels. So if one element turns red, that means it's going to have different sets of energy levels than an element that turns green or blue or yellow or anything along that line. So that's why we need to know about energy levels, and again, Bohr is the guy that came up with that. So that's it for the first part of this section. Let me know if you have any questions.